Guys, to video number 2. What we're looking at here is the case of mass versus weight. Okay, so mass versus weight. First of all, let me let you know that you might want to write this down. Mass is not weight. Okay, these are the notes you're going to want to write down. Okay, mass is the property of an object. It does not depend where the object is located. So look, mass does not depend on object location. Okay, meaning this. Okay, if I were on the moon, my mass would be exactly what it is now. If I were on Jupiter, if I could stand on Jupiter, we know we can't, my mass would be the same as it is now. If I were in space, floating around, the mass would be the same as it is now. That's a property of the object. Okay, it's how much is the measure of inertia of an object. So mass doesn't change, but the thing that does change, okay, and I'll put a little star here, weight does change. Okay, so weight does change, and it depends on location. Okay, so weight does change, and it depends on location. Okay, so let's just figure out what weight is. Let's look at Earth first, and then we can move on to other celestial objects. So up until this point, I've been calling weight I've been calling it F sub W, okay, the force of weight. In the notes, they actually call it the force due to gravity. Okay, if you were to use either one of these, F sub W or F sub G, it would be totally fine. Okay, so here's the deal. Okay, I'm going to write down Newton's second law. Force is mass times acceleration. Okay, we know that weight now is a force. So I'm going to put weight is equal to mass times acceleration of gravity. W equals ma sub g. In some cases, you can actually write it, and it's okay to do this, you can write it as mass times gravity. So look, I'm going to give you a typical, very simple situation where it's asking you to find the weight of a 100 kilogram person. Now, we know from back in the day that gravity is negative 9.8 meters per second squared. So that's the number that we're going to plug in, and I'll put a little asterisk here, for Earth. Okay, and guys, most of the problems we're going to work on, we're going to be on the Earth because that's where we live. So negative 9.8 meters per second squared. Okay, so the weight of this person, this 100 kilogram person, is negative 980 newtons. Okay, so a kilogram, so if I take these units and I multiply them together, a newton, just off to the aside, a newton is a kilogram meter per second squared. Now, what would you rather say, Newton or this whole long spiel? Personally, I'd rather say a Newton, okay? So again, 1 Newton, just to recap, 1 Newton is about the weight of a small, medium apple. Okay, so you realize that the story kind of locks it in where Newton's sitting next to the tree, the apple hits him in the head. It just so happens that 1 Newton is the weight of a small, medium apple. So a 100 kilogram person, which is about my size, has about 980 newtons or 980 apples of weight. Okay, now I know the video is going a little longer than 5 minutes, but let's just take a look quickly at a few things that we can change around. So let's say I were to have weight is mass times gravity. If I give you the weight and I give you the mass, can you calculate the gravitational pull of the planet? Yes. If I give you the gravity, if I give you the mass, can you calculate the weight? Yes. So I want you guys to realize that mass and weight are completely different things, although weight does depend on the mass of the object, multiplied by the gravitational pull of the planet. Now, super quickly, I'm going to say that G sub m. Okay, and some of the questions you'll have to answer, you're going to look at G sub m, and this is the gravity of the moon is equal to negative 1.6 meters per second squared. So the cool thing about weight on the moon is that when you go up to the moon, you're going to realize that you're like a superhero because you can jump higher, you can lift more. In fact, the spacesuits of the people that go up there, the astronauts, the spacesuits weigh on Earth weigh about 200 to 300 pounds. So you're wearing 200 to 300 pounds of this spacesuit, and on Earth it's real difficult to carry 200 to 300 pounds. But then when you go to the moon and you go on the moon with all this stuff on, it becomes really light. So picture it almost as if you were in under the water. Okay, you know how you can lift your bigger brother or bigger sister in the pool? It's almost like that. So you could very easily carry an astronaut just by like curling him with your arms. Very neat. All right, I'll put a link to a couple funny video clips on there for people that do funny things in space. All right, that's it for video 2. And again, these are best played at 1.25 speed. Have a great day.